Space is vast. It's a canvas of endless possibilities dotted with celestial wonders, but the distances are staggering and our current methods are pedestrian. We need a revolution in propulsion technology. Imagine reaching distant corners quickly. Advanced propulsion promises to shrink distances. We must break free from traditional rocketry. Enter the world of propellantless propulsion. In theoretical physics, where reality blurs with mathematics, lies the McGinty Equation. It proposes a radical departure from conventional physics. Imagine the quantum vacuum as a cauldron of virtual particles. This is the essence of the McGinty Equation. It challenges our understanding of the universe. Skywise AI left us a tantalizing trail. Our journey today takes us deep into the heart of the McGinty Equation, a journey to unravel its mysteries and explore its potential to revolutionize space travel. We'll delve into its complex components, from the mind-bending world of quantum field theory to the elegant intricacies of fractal geometry. Along the way, we'll encounter concepts that challenge our intuitions, concepts that seem more at home in the realm of science fiction than in the cold, hard reality of physics. But I assure you, the McGinty Equation, while theoretical, is grounded in sound scientific principles. Our goal is ambitious, but the potential rewards are too great to ignore. We seek to understand how to manipulate the quantum vacuum, how to create ripples in this cosmic ocean that can propel a spacecraft without the need for bulky propellants or energy-intensive engines. So, fasten your seatbelts, engage your curiosity drives, and prepare to embark on an exhilarating adventure into the heart of theoretical physics, where the impossible might just be within our grasp. The McGinty Equation, in all its mathematical glory, might seem intimidating at first glance. Think of the McGinty Equation as a grand symphony, each component playing a crucial role. It describes the interaction between quantum field theory, fractal geometry, and gravity. This warping of space-time is what we perceive as gravity. By manipulating the quantum vacuum, we can alter space-time and generate a propulsive force. Let's start our exploration with quantum field theory. QFT describes the universe's fields associated with particles. The quantum vacuum teems with virtual particles, constantly appearing and disappearing. These particles exist in a superposition of states. Influenced by fractal potential, they create a net energy flow. This energy flow generates a propulsive force. Manipulating space-time at the quantum level influences the dance of virtual particles. Now let's move on to the fractal potential term. The McGinty Equation delves into fractal geometry, a world of infinite complexity and self-similarity. Fractals exhibit self-similarity at different scales. Zoom in and you'll find the same patterns repeating. The McGinty Equation proposes a Sierpinski carpet to create a potential well. This well traps virtual particles, influencing their behavior. It acts as a mold, guiding virtual particles to generate force. The fractal's complexity allows for controllable manipulation of the quantum vacuum. The McGinty Equation, in its quest to unlock propellantless propulsion, doesn't rely on some exotic form of matter or energy. Instead, it turns its attention to the most ubiquitous aspect of our universe, the vacuum of space. But this is not the empty void we might imagine. Quantum field theory, the cornerstone of modern physics, paints a radically different picture. It tells us that the vacuum is far from empty. Instead, it's a seething cauldron of virtual particles, constantly popping in and out of existence like fleeting phantoms in the cosmic night. These virtual particles aren't directly observable, but their presence has subtle yet profound effects on the world around us. They mediate forces, influence the behavior of atoms, and even contribute to the energy density of the universe itself. The McGinty Equation posits that these virtual particles, far from being passive bystanders, hold the key to manipulating the very fabric of space-time. But to understand how, we need to delve deeper into the bizarre world of quantum field theory. The dance of virtual particles. In the quantum realm, particles are constantly in motion, interacting, transforming and annihilating. It's a cosmic ballet governed by probability and uncertainty. Virtual particles materialize, exist briefly, then annihilate, releasing energy. The McGinty equation captures this dance using annihilation and creation operators. By manipulating these probabilities, we can create a net flow of energy and propulsive force. Section 3. Wave vectors and angular frequencies, orchestrating the quantum symphony. Virtual particles like waves on a pond aren't static entities. We turn to wave vectors and angular frequencies to describe their dynamic nature. A wave vector is an arrow showing a particle's direction and momentum. Angular frequency describes the rate of wave function oscillations. This orchestrated dance of particles unlocks the vacuum's energy. Introducing fractals, the geometry of nature. Our exploration now takes us into the realm of fractals. Fractals are everywhere in nature. From trees to coastlines, leaves to clouds, nature loves these patterns. Zoom in, and you'll see the same patterns repeating at smaller scales. The McGinty equation suggests these patterns can influence the quantum world. Fractal potential and the quantum vacuum, a cosmic dance floor. What do these fractals have to do with the quantum vacuum and propulsion? The answer is both elegant and mind-boggling. The quantum vacuum teems with virtual particles. The McGinty equation suggests fractal geometry can influence these particles. This creates a cosmic dance floor, guiding their every move. Section 3. The Sierpinski carpet, weaving a trap for virtual particles. The McGinty equation points to the Sierpinski carpet for propellantless propulsion. Imagine a square divided into 9 smaller squares. Remove the center square, leaving 8 smaller squares. Repeat this process infinitely. The result is the Sierpinski carpet, an endless loop of self-similarity. This fractal can trap virtual particles, funneling their energy. Gravity's subtle influence, a cosmic dance. We've explored the quantum realm and the dance of virtual particles. Now let's turn to gravity, governing planets, stars and galaxies. Gravity, a subtle influence, shapes space-time's fabric. The McGinty equation acknowledges gravity's role. Mass and energy distribution affect virtual particles. The quantum vacuum is like a vast ocean. Gravity creates subtle currents in this quantum sea. Section 2. Mass density, the architect of spacetime's curvature. The key to understanding gravity's role in the McGinty equation lies in mass density. Imagine a sponge representing a region of space. Squeezing different parts makes it denser, like mass concentration. In the universe, mass isn't evenly distributed. Stars, planets, black holes and nebulae have unique mass densities. This uneven mass distribution curves spacetime, creating gravity. Section 3. The integral of influence, summing up gravity's effects. How do we capture the interplay between gravity and the quantum vacuum mathematically? The McGinty equation uses an integral to add up infinitely small things. It represents the cumulative effect of gravity from all mass and energy in the universe. This integral shows how space-time curvature affects the quantum vacuum's energy density. Section 1. Harnessing the quantum sea. The quantum field generator. We've journeyed through the intricate world of the McGinty equation, exploring its theoretical underpinnings. Now it's time to bridge the gap between theory and reality, to translate the equation's elegant mathematics into a tangible device capable of harnessing the quantum vacuum's energy. Imagine a device, a marvel of engineering and scientific ingenuity, capable of generating a localized region of manipulated space-time. This, my friends, is the quantum field generator, the heart of our propellantless propulsion system. This isn't your typical rocket engine spewing fire and fury to overcome gravity's pull. Instead, the quantum field generator operates on a far more subtle, yet potentially more powerful principle. the manipulation of the quantum vacuum itself. It's a device that whispers to the universe in the language of quantum mechanics, coaxing the fabric of space-time to bend to its will, creating a ripple, a wave that can carry a spacecraft across the cosmos. Section 2, a symphony of technology components in harmony. The quantum field generator, like any complex system, is a symphony of individual components working in perfect harmony. Each component plays a crucial role, contributing its unique capabilities to the overall orchestration of space-time manipulation. At the heart of the generator lies the squid array, a grid of superconducting devices known as squids, or superconducting quantum interference devices. These squids are incredibly sensitive to magnetic fields, capable of detecting even the faintest whispers of quantum fluctuations. The squid array acts as both the eyes and the ears of the generator, constantly monitoring the state of the quantum vacuum, detecting the subtle shifts and fluctuations that indicate the presence of virtual particles. But the squid array is more than just a passive observer. It also plays an active role in manipulating the quantum vacuum, generating precisely controlled magnetic fields that influence the behavior of virtual particles, nudging them into the desired patterns dictated by the McGinty Equation. Section 3. Focusing the force. The metamaterial lens. Imagine starting a fire with a magnifying glass on a cloudy day. The quantum vacuum's energy is diffuse, spread across space. The quantum field generator uses the metamaterial lens to focus this energy. It directs energy fluctuations towards the fractal potential well. Acting like a cosmic magnifying glass, it creates a powerful beam. A Sierpinski carpet for the quantum vacuum. Abstract theory must take concrete form. The McGinty Equation's quantum fields and fractal potentials need a tangible nanoscale structure. This structure is the Sierpinski carpet, a fractal of infinite complexity. Nanotechnology lets us build with atomic precision. Our Sierpinski carpet will be etched onto a substrate. For this, we use graphene, a remarkable material. Graphene's hexagonal lattice offers strength and conductivity. Section 2. Electron beam lithography. Painting with atoms. Creating a Sierpinski carpet on a graphene substrate requires a tool of exquisite precision. Enter electron beam lithography, or EBL, a technique for painting with atoms. Imagine a beam of electrons, those tiny negatively charged particles. In EBL, we generate a focused beam of electrons to draw patterns onto a surface. Think of the resist as a photographic film for electrons. The electron beam changes the resist's chemical properties. This allows us to selectively remove areas of the resist. The beauty of EBL lies in its precision. We can draw features as small as a few nanometers. Section 3. Nanometer precision, engineering at the edge of reality. Creating our Sierpinski carpet on the graphene substrate is a meticulous process. We start by coating the graphene with a thin layer of resist. Then, using EBL, we etch the fractal pattern layer by layer. Each iteration involves dividing a square into 9 smaller squares. EBL allows us to replicate this process with nanometer precision. The McGinty equation calls for a Sierpinski carpet with an iteration depth of 5. Our final pattern, measuring just 1 millimeter across, contains squares so small that over 100 billion of them could fit on the head of a pin. Orchestrating the quantum symphony, the control system. Our quantum field generator is a symphony of superconducting squids and a metamaterial lens. This intricate orchestra needs a conductor, a control system fine-tuning this delicate dance. The control system orchestrates energy flow, ensuring every component works in concert. It's a marvel of modern engineering, balancing hardware and software. Sensing the unseen quantum field sensors. Imagine conducting an orchestra in darkness, unable to see or hear the musicians. That's our challenge with the quantum vacuum, a realm of invisible particles and fluctuating energy fields. We need sensors to detect subtle shifts within the quantum vacuum. These sensors are as crucial as a ship's radar in a storm. Strategically placed, they're marvels of miniaturization and sensitivity. The data stream helps fine-tune the generator's operation for precise conditions. Section 3. Adaptive algorithms learning to dance with the vacuum. The quantum vacuum is a fickle dance partner, its rhythms constantly shifting, its movements difficult to predict. Adaptive algorithms, the cutting edge of artificial intelligence, come into play. Imagine a dancer learning a new, complex routine. With practice, the dancer's body internalizes the rhythm, the movements become fluid, effortless. The quantum field generator, guided by these algorithms, becomes more efficient at manipulating the quantum vacuum. Reflecting on the journey from equations to engines. We've reached the final movement of our symphony, reflecting on our extraordinary journey. We began with the need to break free from traditional propulsion and explore the cosmos. Guided by the MEQ, the McGinty Equation, a new beacon of theoretical insights, we delved into quantum field theory, exploring virtual particles in space, translating equations into a quantum field generator, superconducting squids, and metamaterial lenses. Section 2. A universe of possibilities. The promise of propellantless propulsion. Imagine spacecraft without massive fuel tanks. Their journey is limited only by the lifespan of their instruments, reaching the outer planets in months, not years, sending probes to nearby star systems, receiving data from worlds once the stuff of science fiction. Propellantless propulsion could revolutionize space exploration, unveiling the secrets of the universe. Embracing the challenge. The journey towards propellantless propulsion is not without its challenges. The McGinty Equation remains a new theoretical framework on the cutting edge of quantum plus AI. Translating it into a working system requires overcoming significant hurdles. We'll need new materials, refined nanofabrication, and advanced computing power. These challenges are daunting but not insurmountable. Humanity has a track record of achieving the impossible. This pursuit requires collective efforts from all walks of life. Let us embrace this challenge with wonder and excitement.